Good morning, everyone. My name is Avinaya Tripathi. I am a PhD student at ASU, currently working under my PA, Professor Narayan Nethalat. It was supposed to be his presentation, so I'm just filling up for him. So here we'll talk about incorporation of PCM into slabs, concrete to basically measure and kind of prevent cracking. So, like again, whenever you move around in concretes, you'll see different types of cracks. I think this is like quite common out there. So, let me start by introducing concrete itself. So, concrete basically in general consists of cement with water and aggregate. Now, aggregates, there are different sizes of aggregates, different types of aggregates. Even for cement, we have like replacing agents like fly ash, limestone, and there are like modifying agents like plasticizers, accelerators that we use. Concrete generally used like again for different purposes: slabs, dams, bridges, roadways, buildings, everywhere. So there are different types of cracking that happens in concrete. So some are just not aesthetically pleasing, some are structurally deterrent. So with time, some cracks happen initially, while some cracks get developed with time. Some are basically load induced like tension bending cracks, and some are reinforcement erosion cracks that happen. Here majorly we are focused on the thermal cracking of concrete. So how does thermal cracking happen? So cement, when it hydrates, it's an exothermic reaction. So there will be like heat being released from the cement. So this heat causes the cement to expand, and even with the ambient temperature being different, the cement will contract, expand, and when the contraction expansion reaches a stress such that the tensile stress of the cement will be concrete will be exceeded, it cracks. So it's generally assumed that a 35 degree Fahrenheit change on a 1 feet thickness of concrete is enough for thermal crackings to occur. And we generally there's like about a 20 to 50 degree Fahrenheit change in the cement itself due to the hydration. So cracking generally in the sense happens not because of just the thermal change, also because of the restraint that it goes through, because the concrete is not allowed to contract and expand is why the crack happens. If it was free to expand and contract, the cracks may not happen. But now we can't remove the restraints, because if you put a slab on a grade, then there are going to be restraints. If you make a thick structures, there are going to be restraints, right? So the best way is to prevent the temperature fluctuation. So, okay. So the crack, as I've told before, like when the stress goes such that the stress exceeds the tensile strength of the concrete, it's going to crack. So one major way to prevent cracking is to regulate the temperature that the concrete goes through during the hydration. So for that we can use PCMs, phase changing materials. So what are phase changing materials? These are like latent heat capacity materials which can absorb or release heat at certain temperatures without increasing or decreasing temperature. So even water at 100 degrees Celsius to change to vapor will take 2200 kilojoule per kg of heat. But again, for a concrete perspective, we want something that's going to do around 25 degrees Celsius or that range, because that's the ambient temperature usually we deal with. And there are different types of phase changing materials. Some are organic, some are inorganic. So in general, if you consider a candle, it's like burning a candle. So the thread, if it burns in itself, it will just keep burning and end in a short period of time. But now, because the wax takes the heat, it will burn for a longer period of time. So basically similar kind of concept. The solid phase change material, initially the solid takes heat and the temperature rises to a point, and there's a certain temperature where the transition from solid to liquid needs to happen. But initially to change to liquid, it will take a certain amount of heat. So that heat that it absorbs prevents the temperature from increasing. For this work, we tried with two different types of PCM, which we are calling as PCM-M and PCM-E. Both are a paraffixin wax based PCM with different constituents of it. One is a higher paraffixin wax, while another one is a lower with other things. Here, PCM-M, in the size range, this is like a agglomeration of the PCM. So generally the size range of a particle is in the range of 10 micrometers, but they are agglomerating in the size of around 20 micrometers to 300 micrometers, while PCM-E is in the range of 7 micrometers. So we did a thermal energy storage of both the PCMs to see when the temperature, like when it stores the heat. So the range usually said is like 25 degrees Celsius, and we saw like it's the general range that it did. The above one is a heating procedure while the lower one is cooling. So the heating and cooling heat, storage of heat does not usually happen at the same temperature. So there are again different types. In the PCM also there are different ranges of temperature that it can happen at, the phase change happen at. Like one is the two that we are showing here is a phase changing material that changes its state from solid to liquid at around 24 degrees Celsius and another at 35 degrees Celsius. Depending on the use case, we might want to do different PCMs to have different temperature range. If you are doing at a high temperature range, like somewhere in Arizona or somewhere, you might want to use a higher degree PCM, while on a colder kind of region, you might want to use a 24 degree Celsius PCM. And again, it depends on how much of doses that you use. Usually we'll want to use 3 to 5% of PCM, but again, in the work that we are doing here, we have used a higher range of PCMs to show how it works to scale up the thing. So this is a microcity after the PCMs have been mixed into the concrete system. So what we observed was for PCM-M, despite it was again an agglomeration of 20 to 300 micron initially, it does break down during the mixing, but what PCM-M tend to do is it again agglomerated back into a size of in the range of around 300 to 350 micrometers. There were smaller size range also, but again general size range of 300 to 350 micrometers were seen. While for PCM-E, all the agglomeration were lesser than 50 micrometers. So we did calorimetric study on the PCM. So here we see 5%, 20% and 30% of PCM mixed into the concrete. So initially the calorimetry showed that the peak hydration heat release from the concrete decreased with higher PCM values, which we assumed should have been the case. And we also saw the degree of reaction on the concrete, and we saw that there was not much significant difference with the amount of CHS formation on the concrete. As the heat of hydration is lower, the general temperature of the concrete itself is lower with the use of PCM, and we can see that the heat highest peak is slightly delayed by the use of PCMs. So again, this is a heat flow for different doses of PCM. Initially it was just a single PCM, while if you put different PCM, a 0% PCM versus 10% versus 17 to 25% PCM on a concrete mix, what would happen is at a certain temperature, this is a 25 degrees Celsius PCM, so at around 21.9 degrees Celsius, the onset of the storage of heat happened, while the storage of heat happened till around 29 degrees Celsius, where all the solid PCM would have changed to liquid PCMs. The peak was in the range of around 24 to 25 degrees Celsius, as these are 25 degrees Celsius PCMs. So thermal performance wise, we did a shrinkage test, ring shrinkage test. We saw that free shrinkage, PCM did not affect on the free shrinkage and the shield shrinkage for the specimen, but what it did was basically delay the cracking. The specimens did crack, but without the use of PCM, the specimen cracked at 3 to 4 days, while with PCM, it cracked at 7 days. Another thing, initially I told that the cracking happens when the strength exceeds the strain. Basically, when you calculate stress based on strengths, if it exceeds the tensile stress, it will, while the crack should happen. But what we observed was the stress developed were around 50% lower than the actual tensile strength. Again, this could be because the tensile strengths were calculated based on split cylinder test. So they might have been overestimated, but we believe that the cracking happened without the tensile stress being achieved. So with all this laboratory experiment, we did a in-field casting. This is in Arizona. And we did 2 different placements with and without PCMs. We had like temperature sensors, strain gauges embedded in the slabs. This is basically the data acquisition system. It's a Bluetooth based data acquisition system to get the temperature profile in the slab and the strains developed in the slab. This is again the same detailed image. So this was the site where the slabs were casted. Ready mix mixer was brought in to make the mix. The whole dispersion of PCM, everything happened inside the ready mix. So 2 different types of slabs were casted, and we saw the temperature strain development on these 2 slabs. So what we see here is that, so this is just a temperature profile. So temperature profile being that SCP is the one that has the PCM, and the temperature range that it went up to the peak are slightly lower than the peak for a normal without PCM mix. So as said before, so with PCC being the non-PCM slab and TS-SCP being the PCM containing slab, you can see that the highest peaks are kind of delayed and the peaks are not as high as in a non-PCM mix. So this with again, after this we had a numerical model, 1D model developed to see the temperature difference profile and how concrete passes the slab. So this is basically a model of the slab that we casted on the field with a concrete layer placed on a subbase. These were again divided into 50 sections each for the modeling portion. So 2 different scenarios were tested on this, March and a July in Phoenix. So basically March kind of showing a colder temperature range, while the July showing a hotter temperature range. The colors are blue being the cooler color, should have been the next one, but again the graphs are opposite, it seems. So what we did was like with now this is in the range of PCMs that we want to use. Initially we were doing, when we were doing in lab, we are doing 20%, 40% of PCMs just to see the effects. Here the PCMs are in the general range that we will want to use in field. So they are in the range of 2, 4, 5% by volume. So again what we can see is that the temperature range that it goes up to where it is 40 can be reduced by an inclusion of 5% volume. It got decreased to about 35 degrees Celsius, so that 5 degrees Celsius gives us the 5%, it gave us around a 5 degrees Celsius decrease on the temperature range. So based on that, stresses were calculated, the curling stress, all the stresses were calculated, and what we plotted it against was the tensile strength with the stress developed. So there are 4 different test case scenarios that we have shown here. A normal concrete, based on a March colder environment and a hotter environment July. So on a March environment, the tensile stresses developed will not reach the tensile strength of the concrete, but while in a hotter temperature it did, like in the month of July. So again, the top one will not give you a perspective of how it would change the overall theme, but when you see the lower one, initially if it's just normal OPC concrete, you would see that the stress developed reached the tensile strength, while just replacing a 10% of OPC with a 10% PCM gave us a decrease in the stress such that they never reached the tensile stress. Again, as I told before, the cracking in ring test that we saw happened like 50% at 50% of the tensile strength on a 7-day test. So these are right now on the range of 50% of the tensile strength. Same thing can be done by replacing sand also. We can replace, instead of cement, we can replace 10% of sand with PCM. We'll see similar effects, but again slightly they do not see that much different, but again with higher OPC the temperatures are slightly above the one on the second one. And this basically is better than replacing OPC with fly ash, which is supposed to decrease. Like even replacing 20% of OPC with fly ash did not give us as good of decrease on the stress developed, basically strain, which we calculated back to stress. So this work helped us get a laboratory test done on the use of PCM to see if we can dispose PCMs well enough into a concrete mix, and if this could help us decrease the thermal strains developed into the mix, such that most probably we can prevent the thermal crackings that happen in concrete. We again developed a system of sensing the thermal strains based on the strain gauges and temperature profile. A crude model, but at least the initial model to kind of simulate the field thing in a computer-based environment was developed, and again this could be developed further to enhance the prediction of the thermal stress. And finally, I'd like to acknowledge all the funding agencies who helped fund this project.